Our IWCS webinar series event is hosted by the International Cable and Connectivity Symposium. I am Ed Fenton, a cable industry advisor working with the IWCS team. If you have questions, please use the Q&A box on the bottom right of your screen to post a question anonymously. If you wish to contact the presenter or IWCS after the presentation, you will be given the contact points at the end of the webinar. Please note that IWCS does not distribute the presentation slides from either our conference sessions or these webinars. However, please feel free to contact the presenter directly and they will respond individually to you. Today, we welcome Roman Shubochkin of OFS, a Furukawa company in Massachusetts, United States of America, who will be presenting his paper on new generation wideband multimode fiber for shortwave wavelength division multiplexing in Datacom links. Roman Shubochkin is a senior research and development engineer at OFS. He received his BS and master's degrees in optical engineering from Moscow Power Engineering Institute and his master's and PhD in electrical engineering from Brown University in Providence, Rhode Island. He worked as a research fellow at the Fiber Optics and Solid State Physics divisions of the General Physics Institute in Moscow, as well as a senior research associate at Boston University. His research background includes design and fabrication of specialty optical fibers, research on fiber lasers, fiber optic sensors, pulsed solid-state lasers, and rare earth doped glasses. He joined the optical fiber R&D group at OFS in 2012 and works on the design, fabrication, and testing of novel multimode fibers. Roman, we welcome you to present at today's IWCS webinar series event.
Thank you, Ed. Thank you, Connie. Before I start, I'd like to also thank IWCS for the wonderful opportunity to present results of our work to the wider audience. I would also like to thank all the co-authors as shown in the title slide, as well as many, many people at OFS who made important contributions to this team effort. My presentation today is based on results as presented at last year's IWCS conference in Atlanta and as published in the 2015 IWCS proceedings. I encourage webinar participants who are interested in a more detailed account to see the actual paper. The presentation is organized as follows. First, I'll talk about the general motivation for this research effort and development objectives. Then I will talk about the fiber design approach that allowed us to meet these objectives, and then share results on fiber parameters, on fiber measurements, and discuss the results of the bit error ratio tests demonstrating fiber capabilities as an information transmission medium. And then conclusions will follow. So the next slide essentially shows IP traffic growth as outlined in the Cisco VNI index, Visual Networking Index. The annual global IP traffic is projected to surpass 1 zettabyte threshold at the end of this year and to reach 2.3 zettabytes by year 2020. And in case you were wondering, 1 zettabyte is 10 to the power of 21 bytes. And as I found out, the word zetta itself was only adopted in 1991. The compound annual growth rate of that traffic is projected to be about 22% for the next 4 to 5 years. The VNI index itself is driven largely by a combination of video, and that includes virtual reality video, video surveillance, internet video, 2TV, etc., as well as social networking and advanced business collaboration applications. This video impact will be growing going forward. Global IP video traffic will be 82% of all IP traffic by 2020, and that's up from 70% in 2015. As you can see, the growth happens globally across all the world, and the biggest traffic drivers at this point are North America and Asia Pacific, but other parts contribute as well. If you go to the next slide, then what does all this growth means to the topic of this presentation? Again, according to Cisco, if you look at the Cisco Global Index, Cloud Index, it also is growing very fast at the compound annual growth rate of about 25%, and the traffic will triple between 2014 to 2019 to reach about 2.5 zettabytes. An important observation here is that 73% of global data center traffic remains inside data center. Another way to look at it, each byte of IP traffic, as was shown on the previous slide, is driving around 4 bytes of traffic inside data centers. And the rapidly increasing traffic inside data centers will require matching increases in the data carrying capacity of links within data centers. If you look at the statistics of links lengths inside data centers, 90% of them are shorter than 100 meters, and so bulk of those links, optical links, are multimode. If you go to how standards organizations addressed this growth and data center traffic, you can see the plot on the next slide that shows evolution of short reach applications as standardized by IEEE and Fiber Channel. It's a semi-log plot and essentially shows exponential growth that shows no sign of flattening. An important so we're here now in 2016, and the latest standards that were adopted recently by IEEE, it's 100 G-base SR4. Fiber Channel adopted 32 GFC and 128 GFC for SAN applications. 128 GFC was just published a couple of months ago. For both IEEE and Fiber Channel standards, public link budgets spreadsheets are available, and I will mention and will use data from these spreadsheets in future slides. For the future, IEEE is working on 400/200 gig standard. It's out for, I think, first working group ballot. There's a task force working on 25/50/200 gig as well in IEEE, and for this task force, they work on multimode variant of 200 gig, and in turn, Fiber Channel works on 64/256 GFC. So, what were our development objectives early on? And I'll start with the basic premise of a standard multimode fiber. The standard multimode fiber is optimized to work at a single wavelength at 850 nanometers. In fact, it works in a small window around 850 from 840 to 860 nanometers. So the fiber in this window is specified, is rather assured by measuring effective model bandwidths around 850 nanometers. If we go to the principle of shortwave wavelength division multiplexing, it's designed around the idea of introducing additional 3 wavelengths in the fiber, in the same fiber. in order to do that, you need to have a multiplexer, multiplexer at the input of the fiber and the Dmax at the output. The objectives that we set early on was to, first of all, support 850 nanometer legacy OM4 applications. That was very important for us. The question then becomes which way, where are you going to position other three wavelengths? And it was pretty obvious that you have to move to longer wavelengths because there are multiple benefits from the glass system in the fiber, main of which is increased chromatic bandwidth. In order to provide cost-effective solution, meaning cost-effective multiplexer and demultiplexer, it was important to provide wide spacing between these wavelengths, and the input from transceiver makers was that the spacing should be between 30 to 32 nanometers, which is even wider that is used for coarse wavelength division multiplexing in single-mode fibers. And so the choice of the number of wavelengths, again, in this case 4, it rhymes very well with space division multiplexing approach, where you go from single fiber and single transmit fiber to 4 transmit fibers, for example, for 40 gig or 100 gig. So the number 4 or less was chosen as a number of wavelengths. So what that means that the target wavelengths range was that we started to target was between 850 and roughly 950 nanometers, and that makes possible to achieve 100 gig on a single fiber over 4 wavelengths. It also provides migration paths, and I will talk about it later, to generation 2 400 gig speeds, and opens future paths even to highest speed. For example, you can imagine 1.6 terabits per second SR16. If you go to fiber count comparison, as shown on the next slide, and the chart shows example of fiber counts using Ethernet link speeds. You can see what 4 lambda SWDM can do for links. The adopted standards on this slide are shown in white. There are also in pink color current proposals and what standard organizations are working on. But in general, short-reach multimode links operating faster than 25 gigabit per second currently use multiple parallel fibers, essentially, to provide the required bandwidths. So an upgrade from 25 to 100 gig currently requires an infrastructure upgrade from duplex 2 fiber cables with LC connectors to 8 fiber cables with MPO connectors. Same is true when you go from 10 gig to 40 gig. And so first generation 400 gigabit links on multimode fiber will need an increase in fiber count from 8 to 32 fibers. And this is probably as high of a fiber count in a link as is practical. In order for us to go beyond the space division multiplexing and adding extra fibers approach and to increase the wavelength density per fiber, short wavelength division multiplexing around 850 offers a viable alternative, particularly due to the fact that this technology is backward compatible with the existing infrastructure. So it offers multiple future migration paths. For example, it offers migration paths over the same wideband multimode cable plant with duplex LC connections. You can go from 10 to 25 to 50 to 100 to 200 gigabits per second. 8 fiber solutions are very popular today and used both for 40 and 100 gig wideband multimode fiber. opens a path to the next generation or second generation 8-fiber 400 gig solution. It also opens a growth path from duplex 100 gig to 400 gig over 8 fibers, and that's a very attractive proposition. So what are bandwidth requirements for wideband multimode fiber? And EMB here stands for effective model bandwidth. On this slide, in blue line, we have an EMB or bandwidth, fiber bandwidth that is required to close the link budget for 100 meter reach according to 32 GFC spreadsheet. In this case, the original spreadsheet was adjusted for slightly tighter zero dispersion wavelengths and zero dispersion slopes, which means lower total chromatic dispersion, and it was also adjusted for lower attenuation of 3.0 dB. That's lower cabled attenuation. What is important in this slide, it shows that kind of advantage you can gain by moving towards longer wavelengths. You see that in order to get to the same lengths in a link, your bandwidth requirement on the fiber goes down, and that's because you face lower chromatic dispersion, your fiber attenuation decreases, and other penalties like mode partition noise and cross-product link penalties decrease as well. The table on the right shows what TIA essentially adopted as a standard for new wideband multimode fiber. The TIA TR42 group published this standard just 2 months ago in June 2016, and the numbers in bold in the table are essentially showing the spec on that fiber. It's spec'd at 2 wavelengths at 850 and 953. The important number here is 4700 at 850 nanometers. That's the same spec as the current standard OM4 fiber has, and it specifies minimum fiber bandwidths and at 953 nanometers. The red line was adopted as a guidance for to indicate what kind of minimum bandwidth transceiver makers could expect between these 2 points. The worst case wavelengths in this case are 840 and 953 nanometers, and that's similar to on the short end, 840 nanometers. It's again similar to standard OM4 fiber. So now I would like to mention fiber design method, and I'll start with some brief introduction on the fiber parameters. The high-speed communication links that using multimode fiber require that the shape of the refractive index profile of the core to be optimized in order to minimize propagation delays of different model groups and to obtain the highest bandwidths at the operational wavelengths. And the refractive index profile can be generically described as an alpha profile, and the chart on this slide shows alpha. The alpha profile that equalizes delays is called optimum alpha, and the equation for it is shown on the right from the plot. It's also plotted in the blue line. What it does mean that the optimum profile depends on the chemical composition of both cladding and the core, and because of that, it changes with wavelengths. The refractive index profile dispersion is quite significant in standard multimode fibers using standard glass, but that's not an issue because they are designed to have the highest TMB at a single wavelength around 850 nanometers, where blue and the red line intersect. The red line, on the other hand, is the actual profile alpha, which doesn't change much with the wavelengths. So the consequence of that is that the effective model bandwidth decreases for wavelengths away from the peak, as shown with the black curve. This is a simulated curve for the standard multimode fiber. And the green line shows what happens if you decrease dependence of optimum alpha from the wavelengths. And so we designed the fiber using this principle and slightly modified chemical composition of the fiber core. So what that allows us to do, that allowed us to expand that EMB window versus wavelengths. And essentially, we increased spectral widths of the EMB, and that allows us to get higher bandwidths for wavelengths other than 850 nanometers. It assures wider window of operation for the wideband fiber. Now, if we go to the next slide, the slide shows EMB measurements done on wideband fiber samples and compares these results with similar measurements done on two samples of standard OM4 fiber. One thing, the actual data for effective model bandwidths and for overfilled model bandwidths for the blue curve is shown in the table on the right. So we measured at several wavelengths and essentially used VCSEL weighing functions, same weight function as used for 850 nanometers to calculate EMBCs at wavelengths other than 850. So one thing that you can notice that sample OM4 multimode fiber sample number 1 passes EMB requirements for 100 meter each. It passes them not just at 850 where it's designed, but it actually passes them at 950 as well. However, second OM4 fiber fails that 100 meter reach at longer wavelengths. When you install multimode standard OM4 fibers in a system, you do not really know whether your OM4 fiber at 850, how it's going to perform at other wavelengths. And in this case, one of them fails, another passes. If you compare OM4 fiber number 1 and next generation wideband multimode fiber, they have comparable estimated peak and EMB and the EMB around 850 nanometers. At the same time, EMB for the next generation fiber at 950 is close to double of a bandwidth of OM4 number 1, and it's 3 times the bandwidth of OM4 number 2. And this is thanks to the new design of the glass composition for this fiber. On the next slide, I'm showing some measured data on next-gen wideband multimode fiber samples, just standard optical and geometry measurements that were done on multiple samples that were fabricated. And as you can see, all fiber measurements and parameters are well controlled. Essentially no different from nominal specs for standard fiber. Again, this is measured data. This is not a specification for wideband fiber. The design that we used to fabricate these samples was band-optimized design that is fully compatible with the standard band-optimized OM4. Importantly, both attenuation and chromatic dispersion matches that of a standard OM4 fiber. So nothing is negative or different for this fiber than the other one, than standard OM4. However, what it does provide is a much wider bandwidth versus wavelengths window. We used fabricated fiber samples for transmission experiments, and as the next slide shows, we used 4 prototype SWDM TOSAs and 1 wideband ROSA for 100 gig SWDM experiment. The table shows characteristics of both TOSAs and ROSAs at 11 milliamp current that was used to drive them. The VCSEL were driven at this current to push the spectral widths in this test as high as possible and towards essentially worst case 0.60 nanometer value to challenge performance. The encircled flexible for TOSAs is compliant to 100 Gbase SR4 spec. Extinction ratio was more or less around 4 dB for all TOSAs, and wideband ROSA had a good responsivity at all 4 wavelengths within the span of a 100 nanometer window. One channel over 4 channel 20 gig BERT from multi-lane was used to drive TOSA and detect the signal from ROSA. And I also want to point it out that the BERT that we used in this experiment, it had a slightly high intrinsic jitter since it is a model. The model that we had was designed for jitter compliance testing. So, so a lot of in a lot of ways, the way this test was run, it was not necessarily best case situation in this case. The bit rate was 25.78215 gigabit per second, and the signal test pattern was PRBS 31 NRZ in this case. So the standard eye diagrams for the test are shown in slide 15, and as you can see, the optical eyes that I'm showing were recorded using the Keysight scope and 30 gigabit optical head. The eyes, as you can see, remained open after 300 meters of next generation wideband multimode fiber, as shown in this slide. And the thing to point out here that 300 meters reach is 3 times as long as the 100 meter reach specified by the 4 by 25 gig standard. And it demonstrates, excellent, I think, in my view, next generation multimode fiber potential for an extended reach, as well as the general viability of the technology. Next slide shows standard waterfall curves. The bit error ratio waterfall curves of the back-to-back links and also for a wideband fiber at various lengths are shown here, and with sufficient received power, the pre-forward error correction bit error ratio is below forward error correction threshold, which is 5 times 10 to the minus 5, and that is true for all lengths up to 300 meters, and it's also true for all 4 wavelengths. The dispersion penalties at this FEC threshold are less then about 5 dBs across SWM window on 300 meters of next generation wideband multimode fiber. And the penalties for 250 meter transmission are less than 3 dB at a stable operating point of 5 times 10 to the minus 7 BER. So all the numbers I just said are shown on the bottom of the slide. So on the next slide, as I mentioned, this work was done almost a year ago, and back then we did some preliminary tests on the PAM4 modulation, which is pulse amplitude modulation on 4 levels, and we did it essentially on 2 samples, one OM4 that was not wideband compliant, and on a wideband fiber that we made on the next generation wideband fiber. For wideband fiber, as you can see, eyes are wide open. That's not the case for not wideband compliant OM4, which probably is not surprising. We do have more data on PAM4 experiments on wideband fiber, and those results will be presented at IWCS this year. So the ability to successfully use PAM4 on the wideband fiber essentially means that it could be an optimum choice path to 200 gig in a single fiber, and also 400 gig using both shortwave wavelength division multiplexing and high modulation format. So to conclude, shortwave division multiplexing relieves bandwidth challenges in datacom and high-performance computing arena, with next generation wideband multimode fiber facilitating transition to SWM technology. It essentially quadruples linked data carrying capacity, or it allows you to achieve 4 times fiber count reduction. The next-gen wideband multimode fiber future-proofs greenfield cable application installations while being backward compatible with legacy multimode applications. It creates a migration path to achieve 200 gigabit per second per fiber. The next generation wideband fiber provides a more robust path to extended reach 100 gigabit per second duplex links as compared to a standard OM4. And going maybe a little bit further out, it paves the way to the next generation 8 fiber 400 gigabit per second, 16 fiber 800 gigabit per second, and potentially 32 fiber 1.6 terabit per second links. And this concludes my presentation. Thank you very much.
And thank you very much, Roman. At this time, we will ask as many questions from the attendees as time permits, starting with this first question. In view of the dramatic growth in IP and data center traffic, will there ever be a crossover from copper Ethernet to fiber in short-reach applications, or will there always be a copper interface in the networks?
Well, as a fiber guy, I would definitely hope that copper goes away and it all goes fiber. But I think, realistically speaking, for very short reaches up to several meters, there will probably always be a place for copper links. The fiber, multimode fiber, will probably start moving into that area. It depends on the speed of connections, but in my view, for 1 to 3 meter lengths, it's going to stay copper.
Okay. Next question. Are the requirements for short-reach transmission standards evolving at the same pace in different regions of the world? Or will there be differences based on cable technology and design solutions?
Yeah, I believe that the standards are evolving at the same pace everywhere. My sense is it's a global world. You have big population centers coming online and putting demand in different parts of the world, and yet all the traffic can end up almost anywhere. Big data centers, both for redundancy purposes, are spread all over the world. So, to be honest, I don't see those differences based on cable technology or designs.
Okay, thank you. Next question. What was changed regarding core composition? For example, which dope bands were used?
Yeah, I cannot answer this question at the moment. What I can say that there was no significant difference in the final glass. There was no effect on any material properties, but at this point we cannot disclose the dopants.
Okay, fair enough. And let's see, I'm going to ask one final question here and just remind the audience that we have a couple minutes left, but I'm at my last question. So if you do have a question, please submit it now. And the last question is, what kind of laser was used for 850 nm to 950 nm?
Well, if the question is about test laser for obtaining bandwidth data, we used tunable titanium sapphire laser. It's widely tunable from much shorter than 850, and you can tune it beyond 950. So for that particular window, I think it was a good instrument for us to have.
Okay, great. And apologies, I just want to clear. It was a titanium. What was the type again, just to clarify?
The titanium sapphire.
Titanium sapphire. Okay, thank you very much.
Yep.
Okay. At this point, we have no further questions coming in. I wanted to thank you, Roman, for presenting this very interesting and important topic today. Please note the contact points being shown should you wish to contact Roman after today's event. Each of these IWCS webinar series presentation events are recorded and will be archived on the IWCS.org website. It normally takes up to 2 weeks for these to be posted. The IWCS webinar series will conduct presentation events on a monthly basis. Webinar events will take place on the third Friday of each month at 10:30 Eastern USA time. Our next scheduled webinar event will be on Friday, September 16th at 10:30 a.m. Eastern USA time. Each of you will be receiving an announcement for the event a few weeks prior. Please feel free to share our announcements with your colleagues so that they can join in and register as well. For over 60 years, the IWCS International Cable and Connectivity Symposium has been the recognized leader showcasing new technologies in cable and connectivity products, processes, and applications. Our next annual conference will take place on Sunday, October 2nd through Wednesday, October 5th, 2016 in Providence, Rhode Island, USA. Please visit our website at iwcs.org for more event details. In just a moment, you will see a brief survey so that you can provide us your feedback and comments on today's event so that we can further improve this webinar series for you. Thank you for participating, and this concludes today's event.